following movie, we'll create a simulation model of the back cover of an assembly. Here we'll bring the assembly into the simulation tool and we'll create a modal solution. And we'll begin by idealizing the back cover. Now here you can see we have a number of features that we don't need for creating our simulation model, and since the model was created in NX natively, we have access to all of the features. So we can select the ones that we'd like to remove. If we did not have those features, we have other tools with synchronous modeling to be able to remove those features as well, even though they're not features. And here you can see all of those features have been removed and the part is ready to be mid-surfaced. So here we'll go ahead and create the mid-surface, taking the defaults. And you can see it does a very good job. If we take a close look in a few areas, you'll see that there are a few things missing right here. There is a small piece that's missing. And also on the end where the cassette is, you can see that there is some gaps as well. Now we could just trim and create new surfaces in these areas, but we would we can also edit the mid-surface and more easily fix the model. So here we can see, if we take a look at our first face pair, that there is an additional face selected that we don't want in that face pair, and that will help to trim up some of the other pieces. But there's also three separate face pair definitions for the area around the cassette, and we don't need two of those. We'll go ahead and combine those three into one face pair by adding those faces to the remaining face pair. Now if we look closely, you'll see that the mid-surface definition is defined by the side 1 face. We can go ahead and reverse that face pair so that the side 1 face has the blend, and now that looks great. Let's continue by adding those faces that were missed. Here we can see the side 1 faces look good. The side 2 face is missing one of those faces, and that will extend that rib, and we'll do the same thing on the other side as well. Alright, so here you can see we've very quickly and easily been able to fix up a lot of the mid-surface definition. You can see that we still have a small gap here which we can go ahead and fill in with some of the surfacing capabilities in NX. Here we'll go ahead and accelerate the selection of the edges that we'd like to extend using the tangent curves, and the same thing with the limit faces. We'll select tangent faces. And now our mid-surface definition is complete and error-free. We're ready to go ahead and create our finite element model. So we'll go ahead and bring that mid-surface definition in to be meshed. Now before we create our shell mesh, we want to ensure we have a congruent mesh across all of the various faces. So to do that, we'll go ahead and stitch those faces together. There's an automatic pairing algorithm that will stitch edges to edges and edges to faces with the defined search and snap tolerances. Now we're ready to go ahead and mesh. We can define an element size and an element type in the solver environment of Nastran. We can also ensure that our element geometries are good and that we can clean up automatically any small artifacts that may be remaining. So you can see the resultant mesh. We can also interrogate any free element edges to see if there are any areas that are not congruent. Here you can see a close look. Everything looks to be congruent. All right, next we'll define the physical properties such as the material and the thickness for our simulation model. For the material, we've defined that in the master model, and that information comes automatically into the simulation models when creating our digital twin. Now for the thickness, we'll go ahead and inherit that from the midsurface, also reducing or eliminating any chance of error in specifying the thickness of our simulation model. And here you can see the draft that was put into some of the ribs to ensure that the model can be pulled out of the mold. And the different thickness regions in the model. All right, now we're ready to solve for our free modal solution. We won't assign any constraints, but just to ensure that we have a successful solution. And I'll go ahead and pause the solver, but you can see it just takes a few seconds to complete. And in about a minute, we have our results. Here we'll go to the first flexible mode, and we can animate that to visualize the mode shape. And here again you can see the entire model is hanging together. The mesh is congruent. All right, now one of the big advantages of using Simcenter for doing your performance simulation of your NX model is that it's fully associative to the CAD model. So if we go, or if the designer were to make a change to some part of the model, and here we'll do that by going into the back cover component, and we'll move one of the ribs. Let's say that the designer discovered that one of the ribs didn't quite intersect one of the holes exactly, and he wanted to tweak that. Here we'll use the synchronous move face command to do the change. We'll use the face finder to select coplanar faces to expedite the selection of the faces that we'd like to move. Here we'll define a direction for moving those faces. And let's go ahead and line it up so that we can see when we'll be centered over the hole here. And it looks like just about 1/2 of a millimeter, and we have it. Now this change then will flow through into our simulation models. It will automatically update our mid-surface definition, which we'll take a look at next. So here you can see our mid-surface model reflects the change and is centered now on the holes. Next, going into the finite element model, it will update the geometry but not the mesh automatically. Here we can see that geometric change as a wireframe definition, or unshaded. And if we rotate the model a little bit, we'll be able to see that a little bit better. So there you can see the change, and we'll go ahead and update the finite element model to reflect that. Now it will automatically remember that we want a congruent model. It will automatically stitch all of those faces together so that we have a congruent mesh as a result. Also, all of the changes that we needed to make to the midsurface from the standpoint of making those changes has also been preserved. And here you can see the free element check shows that we do have a congruent mesh. And we can now do another trial solve. We'll go ahead and clone the original solution so we can maintain the original results and then compare those to our updated model. So here I'll go ahead and pause the solution again. In about a minute we'll have our updated results. So here we'll open up the original and the updated model, and we can view those results side by side. Here we have the original on the top and the updated one on the bottom. We'll go ahead and synchronize the top and bottom views, and we can animate that as well. Next, we'll see how the structure performs during a drop test. We'll begin by creating our advanced nonlinear solution. We'll give it a name, and we'll select that we'd like a large displacement simulation and run a nonlinear dynamics subcase with a specific time step and number of increments. Once we have the solution defined, then we can define our initial conditions. We'd like to put an initial velocity on the assembly, and we'd like to specify that direction with a coordinate system that corresponds to the contact element that we'd like it to drop into. Here we can specify an initial velocity and put those in whatever units we're comfortable. We'll do 4 miles an hour. Next, we'll specify that the ground will be fixed, and we'll select that by selecting the element and its related nodes. Next, we can specify our surface-to-surface contact, and we'll begin by selecting those faces on the assembly that we expect to contact the ground. And for the target of the contact face pair, we'll select the ground, and we'll make the ground rigid. And here you can see the markers for that contact face pair. Next, we'll create a contact face pair for the view screen in the chassis. Here we'll select the tangent faces around the perimeter of the view screen, that will be in contact with the tangent faces around the perimeter of the chassis in which the view screen resides. Now, for the last contact pair setup, we'd like to specify that between the battery and the battery's housing. So for that, we'll select the related faces to the body of the battery, and then the housing faces that it will be in contact with. And we'll go ahead and complete that selection. Now we've completed our contact definition. You can see why we selected the bottom face for the housing, because of the surface normal direction of the housing for the battery. Now we're ready to solve, which I've already done, and we'll take a look at those results. First, we'll look at the displacement results, and we'll animate across iterations so we can see the nonlinear dynamic results. You can also take a look inside of the housing to see what's going on with the battery by clipping away part of the model. Now you can see the impact of the battery inside the housing. You can also take a look at our stress results. And most of the stress results are going to be at the end of the assembly that's in contact with the ground. And the same thing for our contact results. Next, we'll look at the response of our system due to a motor imbalance. We'll begin by defining the location of the motor. And then we'll tie that location down to our structure. Now that we've defined where our motor location is, we'll set up our response dynamic solution. And then also define where our enforced motion location will be, which is at our motor. And the primary direction for the motor imbalance is in the X direction, DOF1. So we'll constrain all degrees of freedom except DOF1, which will be our enforced motion direction. Next, we need to tie the view screen and battery to the rest of the structure. Currently, it's not connected. So we'll connect it using surface-to-surface glue. And we'll define our surfaces using the tangent faces selection so that we can select many faces with a single click. And this will tie the perimeter of the view screen to the perimeter of the structure. Here we can set a search distance because there's a gap. We'll ensure that that search distance we'll be able to capture those faces. We'll do the same thing for the battery in its housing, selecting tangent faces as well as the end face of the battery. And we'll glue that to the faces in the structure that are adjacent to it. Here we'll set an appropriate search distance and create our glue. All right, now we'll solve our response dynamic solution to get our mode shapes. Here we can monitor the progress of the solution. It only takes a few seconds. Since it's primarily a shell model, there are some solid elements with the view screen and the battery. So after about 20 seconds, we have our first 10 modes. We can view those results as well. You can see our first mode is at 125 Hertz. And we can view those modes. There's our first mode. You can see how it's constrained by the motor location. Second mode, third, and our fourth mode. So those look good. Let's move on to creating our response simulation. And here you can see our 10 modes from our initial solution. You can see the percent mass contribution in the various directions and the total effective mass as well for those 10 modes that we've captured. Next, we'll assign a damping factor to all of the modes. And then we'll evaluate the transmissibility of the structure. And we'll take a look at if we were to accelerate our motor location, what would be the acceleration at another location on the structure in that direction across a frequency range from 0 to 1000 Hertz. So this gives us an idea of the sensitivity of the structure to an excitation and its response at a specific location. Next, we could create a power spectral density function which would characterize the motor excitation, but we already have that from Simcenter test, which from our test lab was able to determine the motor excitation. So we'll go ahead and use that by creating a new event for frequency analysis. And we'll select our motor location. And here you can see our PSD from test lab for the motor excitation. And now that we've set up that event, we can go ahead and evaluate both contour as well as function response. We'll go ahead and take a look at contour first for our stresses within the structure. And here we can select a point from either the XY graph or the various natural frequencies that were determined earlier. We'll go ahead and select the first mode and evaluate the stress based on that frequency. So here, to better see what's going on with the max stress, let's go ahead and take a section cut into the model. And now we can see where our max stress is occurring near the attachment of the motor into the structure. And we can also adjust the units of the stress that are displayed in our results from megapascals to PSI. All right, next we'll take a look at the function response at a specific node for acceleration. And here we can see the acceleration of the node as a function of frequency. And here again, if we don't like the units on the y-axis, it's very easy to go and edit those units to get them in whatever units we are comfortable. So here we'll put it in G's. And that concludes the demonstration.